Okay, my friends, so we're gonna look just at the blue dice here. I didn't make 5 different spreadsheets, one for each of the die colors, because if you see it for the blue dice, you'll definitely understand it for any of the dice, and actually for any data distribution, not just that can be contained on 6-sided. Here they are. These are called nets of dice. You can actually see what's on the blue dice. So you can see there's an awful lot of 5s and 6s, more than there should be on typical dice. There's the average and the standard deviation that we've been chatting about. Now, again, those are population parameters, which means you wouldn't actually have them. What you also won't have is this. This is a distribution of the sums on those 6-sided dice. The one thing I want you to check, the vertical axis is not a frequency axis like it was in the last video. I've changed it to a probability axis. Which it doesn't change the mathematics of what we're about to do. It just drives home the point of relative frequency, which I think is going to become more important as we compare larger and larger sample sizes. So each of these probabilities corresponds pretty nicely to the ways that you can get certain things. Like, for example, there's only one way to get a sum of 2 back on these dice. You have to get that one and that one. That's it. There's no other way. There's also only one way to get a 3. That's why the chance of a 3 and the chance of a 2 are the same, because you have to get that 2 and that 1. There's only 1 out of 36 ways. As far as a 4, it looks like there's 2 ways to get a 4. Let's figure it out. You can get that 1 and that 3. Or you could get that 1 and that 3. There's actually 2 3s on this die. So that 1 paired with either that 3 or that 3. And that gets you your sum of 4. And as much fun as it is to try to figure out all the different ways we can get the sums over here from the original dice, let's just stop here, realize we could if we needed to, and move on. Because remember, that's all fiction, right? All of this is fiction. You're never going to see that. You're never going to see that. What are you going to get to see? Well, that's where it gets fun over here. Now again, let's make this, I'll make this graph a little bit bigger. Okay, so what you're seeing now, what I've done in this particular sheet is I've replicated what you did in your homework from yesterday. So in other words, I've sampled, you can see it if I move this over here, groups of 4 rolls at a time. And I can re-randomize this. Every time I press F9, I get new random draws from the blue dice. Remember, this is just the blue dice. I'm not talking about the red, orange, green, or yellow at this point, just the blue. Although it doesn't matter. The same thing will happen for any of them. So what you're seeing is just a more robust version of what you did in your homework. Every time I press F9. Notice those graphs are not changing very much. You know, you're seeing the majority of the data is happening right around here. You've got a bell shape. Every once in a while you get a little goofy outlier like the one that's down here. But by and large, you're not getting into the tails with that 2 and 3 and 12 up here. We'll talk more about that as we go. So also remember, the average of our population was, what was it, 8.2. If you look in this graph, where 8.2 is, it's always near the tallest bar. 8.2 is right about here. And notice that the tallest bar is always near that 8.2. What that tells us is, on average, the sample mean we're getting from a sample of size 4 is quote-unquote close to the population average. Now, I know what some of you are thinking. You're thinking, yeah, there's a chunk of data here, but there's also quite a bit of data over here, which is really nowhere near the average. And this is what I wanted to mention. I wanted to mention, well, this is assuming a sample size of 4. Let's bump the sample up to 9. Okay, here's a sample of size 9. Same basic idea, except now I'm grabbing 9 rolls. You can actually see them over here in these cells back here. Same exact idea we just did, except we increased the sample size from 4 to 9. But same principle. And you might notice if you click back to the 4 and the 9, what just happened? Well, 2 things happened, really. And I think they're mathematically tied to each other. Over here, the tallest bars are near that 8.2. Well, that hasn't changed here. The tallest bar is still near the 8.2. You can see what's going on. But this curve over here is wider on average than this curve here. Notice how when the 4 sample size, you've got data down here in the 3 and the 4 and the 5 range, and over here in the 11 and the 10 range. When we click over to 9, those extraneous ranges are starting to fall off. Well, remember that 100% of the data has to be in each of these curves. If you're losing tails, that means that probability has to go into the middle. So let's look at the probabilities to actually understand why. These tallest bars, when n equals 4, are hovering, what's that, 14, 16%. Yeah, they're hovering up there at 14 or 16%. The tallest bars now are around 20%. So all that extra tail probability gets closer to the average, which is pretty rad. That tells us that we are more likely to get closer to average with our sample when the sample is larger. Let's keep going. Let's go to a sample size of 16. Okay, same exact idea as before. Drag this thing out so we can see it better. There we go. Very good. And again, same pattern is happening. Same pattern is happening, except look at that top bar now. Those top bars are pushing up towards 30% now. That means we picked up an additional 10% from the tails and are bringing them closer. I mean, just look at the distances between the extremes compared from size 4, which the extremes go from 4 up to 12. And now in 16, the extremes go from 6 up to 10. We're reeling in the outliers, so to speak.
Hey y'all, just wanted to stop here real quick and give you kind of a more concrete explanation as to why the tails are going away and why the middle is growing. We've grown accustomed to saying things like larger sample sizes mean margins of error shrink. But at the same time, there's a very sound mathematical reason for that. For example, with these dice, in order to get into the extreme tails, the 2, the 3, the 12 on this side, you have to repeatedly hit very unusual events. For example, that's the only way you can get snake eyes on these dice, because there's so many other 5s and 6s and 3s and stuff like that. So to hit snake eyes once on this dice, once on this pair of dice, happens 1 out of 36 times. That's 3% of the time. Okay, that's pretty rare. Hitting it twice would be 3% of 3% of the time, which would be 0.09%. So you go from 3 times out of 100 to 9 times out of 10,000. And to hit it again, that would be what? 27 times out of 1,000,000. And to hit it again, that would be 81 times out of 100 million. So you can see, and that was only with a sample of size 4, right? I rolled it 4 times. How about 16 times? You see what's going on. So another good reason the tails disappear is that it becomes harder to randomly, repeatedly select the unusual values. They're unusual for a reason. They don't happen very often. So if they don't happen very often once, they're sure not going to happen very often a whole lot of times. Hope that made sense.
Okay, let's go over to a sample size of 25. Same thing happening. We're getting, it's just, the curves are tightening up. That middle bar is now pushing over 35. Look at that. 35, sometimes as high as 40. Let's go to 100. Now this is crazy. I love it when we get to 100, because now at this point there's like, 4 bars, one of which is barely there. Occasionally you might get another one up there above 9. But what's totally cool about this one is, I'm going to goof with this a little bit here. I'm going to click over to this other tab that says n equals 100, a closer look. All these graphs back here have broken up the ranges by a half. 2, 2.5, 2.5, 3, 3.5, 3, 3.5, 3.5, 4, and so forth. That works here too. The problem is, of course, is that all the data is now basically in the 8 to 8.5 bar, which of course you knew, because the averages should be in that bar. And look at that, 65% of all the data we're getting is in the bar we need to be in. That doesn't mean the bell curve is gone. You might look at that and go, wait a minute, we were seeing bell curves, bell curve, bell curve, bell curve. The bell curve's gone. It's still there. If you just make the horizontal axis more refined, instead of making it a half wide, make it a 1/10 wide. The bell curve is still there. It's absolutely still there. As a matter of fact, looking at it with this level of precision down like this, And it's pretty cool. You can still see where the population average is, right? It's still around this 8.1, 8.2, 8.3 bar area. At this point, I actually tried to make a sample size of 10,000, but I realized it's just too much going on in the spreadsheet, and I'll explain why I tried to do that in a second. But I think now I want to go to the next video and explain to you the big idea behind increasing those sample sizes the way I did. Yeah, you already knew that the margin of error in the sample was going to shrink, and you saw it. These curves, these sampling distributions keep getting narrower as the sample sizes grow up. I mean, you knew that. We've been talking about that since about week 2 in this class. But what's totally rad is they get smaller predictably. Let's take a look.